button. Get out of the way. All right. So let's go ahead and warm up with this question. And then we're gonna do one more thing on PK. And I'm gonna introduce you to the next section, which is nucleophiles and electrophiles. So let me put some lone pairs in here so we can keep that part straight. So we got lone pairs there, there. All right. And then so now the question becomes, if we are we looking at these as acids and we don't have uh the pKa, right? What do we how do we compare the acidity? And it's this hydrogen in each case, one of the hydrogens that's on that. And I think one of the things that kind of slows people up when we talk about acids and bases, when you're looking at an acid, it's always you always want to try to figure out what the acidic proton is. Is usually the proton that's connected to the most electronegative atom in that molecule, right? That's going to be your acidic proton. So I heard somebody say it. Uh, what we normally use is what?
Hires.
Hires, right? And what we want to do is look at the conjugate base for each one of these. Is that right? So the conjugate base, come on, Russell, get it together. Conjugate base for acetic acid looks like this. This is one we did already. Is that right?
Yep.
And then the conjugate base for the next compound would look like this. Right? And then for the sulfonic acid, look like that. And then the last one would look like this. Right, so those are your 4 conjugate bases. Now, what are we comparing uh, in each case? What can all of these do?
Resonance.
Thank you. They can all do resonance, right? And then in every case, the negative charge is on the same atom with the exception of nitrogen. So electronegativity is going to play a role, but the size won't necessarily play a role. And there's really not any induction that's going to play a role. And the hybridization state of each atom is the same, right? So we don't have to think about hybridization or induction or size, because oxygen and nitrogen are not that far apart in atomic radius. So it's really going to come down to resonance and electronegativity. Is that okay?
Yes.
Yes.
All right.
Quick question.
Go ahead.
So, just as a quick refresher, how can we know off rip that all of them can be resonant?
Well, you see this pattern right here, right?
Is it because you can move? Okay.
It's the same allylic anion type pattern.
Okay.
All right. And so if you have that pattern present, then you know that you can do resonance. Right, so I'm just going to put the arrows in. You can draw the resonance forms in. All right, you can do that. right? So all of them can do resonance. All right. Now let's think about what a charge is. So the charge is on oxygen in 3 of the 4 cases, and then on nitrogen in 1 of the cases. So which one of those do you think is going to be the weakest out of all the acids based on where the charge is in the conjugate base? Right? If we're comparing nitrogen to oxygen, right, what would you expect? Say again?
Nitrogen.
You would expect this to be the weakest. Is that right?
Yeah.
Why? Would it be because of the electronegativity difference?
Yes.
Yeah. So when you compare, so now you got resonance and electronegativity, but now since they can both do resonance and delocalize the charge, we need to think about another factor. And in this case, it's going to be electronegativity. Right? All right. Now let's think about which one of these do you think is going to be the strongest acid? Right? Oxygen has the same electronegativity no matter what in all 3 cases. So what's different? Let me help you a little bit. What's different about this acid compared to the other ones?
You have a sulfur.
Okay, you do have a sulfur. I agree with that. There's something else
There's
that's
another
different
double
too.
bond.
As another pi bond. So that means you can do what? You can do resonance more than once. Is that right? You can do resonance here as well as here. Is that right?
Yes.
What do we know about resonance as it relates to stability? The more resonance forms you can draw, the more stable the conjugate base is going to be. Are you following? So when we compare that acid to the other 2 acids, what do you think that's going to be our strongest one?
Yeah.
Yes. All right, so this is going to be our strongest acid. And then now let's think about the other 2 acids. All right, so we know what our weakest is, we know what our strongest is. Now let's think about the other 2 acids. What's the difference between those?
One has a sulfur and one has a carbon.
One has a sulfur and one has a carbon, right? So what do you think? Do you think that the acid containing the sulfur is going to be a better better acid or a worse acid?
Better.
You think it's going to be better? I tend to
Yes.
agree. I think that the ranking is going to be from the sulfonic acid here, and then the second sulfur containing acid, followed by the acetic acid, and then the amine. Now we can look these up too to verify. I like doing that because it helps to add a little more punch to the explanation. So I gotta actually, let me see. Let me pull up something real quick. One of my other programs. So we know this is acetic acid. So we know the pKa of that is about 4.7 pKa. And then this we're gonna call acetamide or acetamide. So let's see what we can, somebody can see if you can pull up the pKa for acetamide. And then somebody pull up the pKa of methane sulfonic acid, which is going to be this.
For the acetamide pKa is 17.
17. Okay, cool. Which is, it's not a horrible pKa for amide, but normally NH protons are somewhere between 30 and 50, but because of that, you're able to do resonance. That's why you see that pKa being roughly, a little bit lower than what you normally would expect. So 17. Anybody got methane sulfonic acid?
Negative 2.0.
Negative 2.0. Very good. I agree with that 100%. And then the last acid, let me look that up right quick. Let's see. Just throw this in this program right quick. The name is escaping me, so I gotta look it up. Let's see. Let me look it up. Okay, so it's methane sulfonic acid. Let's look that up. pKa. Maybe on this table here. Let me look that up right quick. Somebody else can look it up too. It's methane sulfonic acid. Probably gonna be somewhere in between 2 and 3. Yeah, we're gonna say that the pKa is around 2. Right, and again, you can think about that sulfur because of the size of it. It also helps to kind of delocalize that charge as well, even though you're also delocalizing it through resonance. So that's probably why you see the sulfonic acid and the sulfonic acid have much lower pKa's than the carbon-containing acid, like acetic acid, right? Because if you look at acetic acid, which is 4.7, and then the sulfonic acid, which is around 2, somewhere around 2, right? That's still 100 times more acidic, even though the pKa difference is not that great when you think about it from in terms of the difference in acidity. It's about 100 times more acidic, so that's a lot. Let's stick a date over here. All right, so let's do one more
Question.
Go ahead.
Does the symmetry in methane sulfonic acid, does that somehow make it stronger?
No, I don't think
not really.
No, I don't think it's the symmetry, because if you really drew it out, it's actually bent. It's actually not linear like that.
Mm-hmm.
So I don't think it's the symmetry more so than it is the fact that that negative charge on oxygen is really, you can delocalize it more than one way.
Okay.
Yeah, because that's all your acidity is always going to come down to how stable the conjugate base is. And in this case, with you being able to do multiple resonance forms, then that immediately points to a higher level of stability than something where you can do less resonance forms or generate less resonance forms.
Okay, thank you.
All right, good question. That's a great question. I like how you're thinking. Let's jump on to this worksheet right here. Let me put the date up here so when I post the notes, you'll know where we were. All right. So this is a great way to finish this out because all of the topics are in here, like the equilibrium prediction, the difference in acidity, the hires, all is all wrapped up in this assignment right here. So somebody look up the pKa for triflic acid, and then somebody look up the pKa for toxic acid, or you might, if you can't find toxic acid, you can look up toluene. Let me make sure I write it the right way now. Sulfonic acid. And then triflic acid. You'll be able to find triflic acid. That ain't gonna be a problem.
For triflic acid, it says -15.
Okay, we'll take it. We'll take it. Yep, we'll take it. -15.
Yeah.
Put that right here. So -15.0. That, and I've used triflic acid before. It's so acidic that when you take the top off the bottle, the vapors they react with the water in the atmosphere, and you can see the reaction happen. It's very, very acidic. So it's exchanging, doing proton transfer with the water that's in the air. It's that acidic. All right, what about toxic acid? Anybody got that? Or toluene, sulfonic acid?
I don't know if this is right, but it says -1.34.
That's about right. That sounds about right. It's also very acidic. I'm saying -1.3. We'll take it. Yeah, we'll take it. All right. So now down here it says explain the pKa difference. How you going to explain the pKa difference? What's the first thing you need to do to look at why the pKa between two acids, the pKa's are different? What do you need to see?
How many more times acidic it is? Like
That's only going to tell us that value, right? It's only going to tell us, oh, it's 16 times more acidic, or it's 1,000 times more acidic, 14 times more acidic.
This one we use hires?
Yeah, you have to look at the conjugate base. Is that right? So for this conjugate base, it's going to look like this. Anybody disagree with that? The conjugate base is the acid after it's lost a proton. Is that right? Yes or no?
Yes.
And then so the conjugate base for toxic acid is going to be SOOO minus. And I'm going to put, never mind, I ain't going to do that. I'll draw. I don't want to be lazy. That's what the conjugate base for that looks like. All right. So now how do we explain the pKa difference? What are we looking at? We're looking at the atom where the negative charge is. Wherever that atom is in the conjugate base, that's the atom that we're looking at to see how am I going to stabilize this negative charge. All right. What can both of those do immediately? If we think about, well, let me not ask that question first. Let me ask this question. What can we rule out of our 5 factors?
Size.
Size, we can rule out size. I agree with that.
And hybridization.
Hybridization, both of them are sp3 hybridized.
Resonance too.
Well, they can both do resonance, and they both have the same number of resonance forms. Let's show that. That's great. I'm glad you said that. So we can do this and this. Is that right? On both?
Yes.
And then we can also do another resonance form where we go here and here, right? They're not happening at the same time, so don't trip out about that. It's just the fact that you can do it more than once. So really, we can rule out resonance as the stabilizing factor because that's only one of the stabilizing factors, right? What else? Isn't isn't the fact that the negative charge is on the same atom in both conjugate bases? Can we rule out electronegativity?
Yeah.
Mm-hmm.
Yeah, because it's the same for both, right? Oxygen, it doesn't change. The size doesn't change. The hybridization state doesn't change. And so both are stabilized by resonance. I don't want to rule out resonance. I just want to say that they're both stabilized by resonance. So I'm gonna say that. Both are stabilized by resonance. I'm abbreviating that. All right. Now, what about induction? What is induction? Somebody help me. Sound like I'm in church.
When you when in I just know fluorine creates a dipole because it's more electronegative, so the electrons are gonna orbit more around that atom.
All right. So the fact that you have this is induction in a nutshell. You have an electronegative group of atoms, or atom or group of atoms, close to a charge that's able to delocalize it by doing what you just said it, creating a dipole or creating some polarity. Is that right?
Yes.
All right. So you got this big giant CF3 group proximal to your oxygen, and so you're gonna have a huge dipole going this way, right? Because of the CF3 group. Do you have that over here?
Yes. It's just further away.
Well, no, that's a CH3 now. Let me fix that.
Oh, my bad.
That's okay. But if it was a CF3, you would be right. It would be further away. I'm about to write. Oh.
Dr. Russell,
Yes.
I thought when you do induction, like you focusing on the oxygen atom or the central atom that
Where the charge is?
yeah.
Yeah, we
I
are.
feel like the dipole should be longer, right? Like from oxygen to fluorine, right?
Oh, you
Because
just.
it's like it seems shorter, like it's like
Oh,
coming from the other oxygen.
all right, we can do that.
I was just making sure I wasn't like understanding right.
You just felt like just throwing some salt in the game. That's all right. We can make it longer. Cause I get what you're saying though. The electrons that are being polarized are on oxygen.
Yeah.
So yeah, I'm with you. I'm with you.
All
We're on
right.
the same page, swimming in the same pond.
Hmm.
All right. So how do we explain the pKa difference? What factors stabilize the conjugate base of triflic acid?
Induction.
Resonance and induction.
Resonance and induction. What factors are stabilizing the conjugate base of toxic acid?
Just resonance.
Just resonance, right? So the triflic acid is a stronger acid because what? How do we finish that sentence? The triflic acid is a stronger acid because
It's stabilized by both resonance and induction.
and induction. Very good. Good job. Yeah. So it's stabilized by both resonance and induction. All
We
right.
would say the conjugate base is stabilized.
Yes.
Right.
Triflic acid is a stronger acid than toxic acid because the conjugate base is stabilized by resonance as well as induction. Strong induction at that, because fluorine is a very highly inductive group. So it can really take that electron cloud that's sitting around oxygen and really pull a lot of that electron density towards itself. All right. Okay. Now let's go to this part 2, the number 2. All right, I'm gonna erase the hardest part. Number 2 asks a question. It says, how much more acidic is one acid than the other? So what do we need to do? We need to find the difference in the pKa, don't we?
Yeah.
Which is what? If we got, we're going to do the absolute value now because that number can't be negative. So we're going to say negative 15 minus negative 1.3, which would be what? 13.7. Is that right for the difference in pKa? Yes.
Yes.
So what do we do with that information? If the log of x, brain working faster than my fingers, log of x equals 13.7, then x is what? 10 raised to that. And it's okay to round up. So 10 to the 14th. It's a lot, man. What is that? 10 to the 14th. 6 is a million. 9 is a billion. 12 is a trillion. So it's what, 10 trillion? Something like that?
Yeah, something like that.
Yeah, that's a lot. Right? What does that mean in terms of how fast H plus is coming off of triflic acid compared to toxic acid? Because we did mention that or talk about that. What does that mean? It means for every one proton that comes off of toxic acid, how many are coming off of triflic acid?
10 to the 14th.
10 to the 14th. Right? That's a big, big difference in acidity. Huge difference. All right. Let's go to the next question. It says, what does the answer to number 2 say about how readily the proton is removed from the stronger acid? So we know we said that triflic acid was the stronger acid. What does that say about that? Stronger acid. What's another way to say that?
A.
That is rapidly deprotonated. That's exactly right. What's another way to say it? A strong acid, when you're talking in terms of its conjugate base, what's the way to say it relative to the conjugate base? A strong acid has a stable
Weak.
or unstable?
Oh, stable.
Stable conjugate base. Good. That's the question in number 4. What can we say about the conjugate base of the weaker acid?
It's still C.
Yeah, less stable. That's right. Weak acids have less stable conjugate bases. And then again, when we talk about stability, we're talking about wherever the charge is or the electrons are in that conjugate base, how they are delocalized. The more I can delocalize them, the more stable the conjugate base is going to be. All right, let's do number 5. It says HA has a pKa of 15, and then
Doctor, can you zoom out?
Yeah.
I mean, back to the top, because I don't have the worksheet. Like I said, I ran out of ink, so I'm trying to copy this. The questions and answers.
Dr. Russell, can you scroll up a little bit more to the one in red? Thank you.
Mm-hmm.
Okay, I'm done.
All right. Everybody got what they need? We good now?
Yes, thank you.
Yes.
All right. All right. Let's go down to Number 5. Let's read the question. Somebody read the question. Use that good high dollar microphone on your laptop. And let's see if we can figure out what this question is asking.
HA has a pKa of 15.
Okay.
HB has a pKa 5.
Okay.
Draw the equilibrium that will result from mixing HB, which is the acid, with Na
Mhm.
and
Okay.
predict which side would be favored. Show all arrows.
Okay. So we're taking HB plus Na plus A minus, right? Is that clear? When it says HB and NaA? All right. And then we're trying to predict the equilibrium. So let's put the arrows in first. This is a proton transfer mechanism, which means that the electrons on A are going to be used to attack H. Follow?
Yeah.
And then I'm going to break the bond between B and H. So on the other side of my arrow, I'm not going to put the arrows in because we got to predict the equilibrium. We'll have what? HA plus Na plus, and then B minus. Anybody not following that? All right. So what information do we have? We have the pKa for HA, don't we?
Yes.
Which is what?
15.
pKa of HA, good, is 15. And then we have the pKa of HB, which is what?
5.
5. All right. Oh, that equal sign is horrible. Sorry about that. All right. So now we've put the arrows in. We know the pKa's. Now we just need to predict the equilibrium. How do we do that?
The equilibrium favors the weaker acid, right?
Exactly. So again, we can do the seesaw method, right? Or if you already know, somebody tell me this. I heard the person, who was that who answered?
Krista?
Okay. Tell me, how do you know the acid is weaker based on the pKa?
Because because the pKa is 50, right?
Say again, the pKa is larger?
Yeah.
Yeah,
It's 50.
that's right. It's not a trick question. It's just designed to make you think about it a different way. So a higher pKa corresponds to a weak acid, and a lower pKa corresponds to a stronger acid. So when you have an acid-base equilibrium, the equilibrium is always going to favor the weaker acid. Why? Somebody tell me why. What is it about what does pKa tell us again? Anybody? Does it tell us how acidic an acid is, or how good of an acid is a Bronsted acid is?
Yes.
Yeah. And Bronsted acids do what? Anybody?
Donate protons.
They donate protons. So a strong acid is going to donate protons readily. A weak acid, not so much. Is that right?
Yeah.
Yes.
So why is it important to understand that the equilibrium is going to favor the weaker acid? If you're going, now keep in mind, equilibrium means you can go back and forth. Is that right? You can go from products back to reactants, reactants to products. Yes?
Yes.
So why is it important that the acid that you're making in the product side be weaker than the acid you started with?
Because the weaker acid isn't going to give off protons as much as the original acid would.
Good.
So
Then your reaction won't go back to.
Right. If you make a weaker acid, then the reaction is not going to go backwards back to the start materials, because a weaker acid is not going to give up H plus as readily as a stronger acid. Does that make sense?
Yep.
Yeah. So that's why it's important to understand it from that perspective of favoring the weaker acid, because you're trying to you want the reaction to go from reactants to products, not the other way around. All right, we okay with that?
Yes.
All right. Any questions about that? Like I said, this little worksheet here kind of combined all our concepts into one place. So that's a good thing. Any questions about hires? Any questions about anything? Let me put the date right here.
I have a quick question.
Go ahead, Amar.
So when we're looking at induction,
Yeah.
and we're looking at what is it? 4, like the fluorine, oxygen, and the nitrogen.
Like, are you talking about like hydrogen bonding?
Yeah.
Okay, go ahead.
Do they have like an order to it? Because I know a second ago you were talking about like fluorine has a really strong dipole moment. So does that mean like oxygen has a weaker one?
It's only weaker because of the electronegativity, because it's lower. Fluorine is the most electronegative atom on the periodic table. It has an electronegativity of 4.
Mm-hmm.
Oxygen is 3.5. It's the second most electronegative atom, right? So it's only if oxygen is doing induction, it's only less than fluorine because it's a little bit less electronegative.
Okay, but oxygen would still be greater than nitrogen.
Yeah.
Okay, cool.
Yeah.
Oh, she got big legs.
Huh? Where'd that come from? Mute y'all, man. Y'all Ryan be talking about everything. All right. So we got 10 minutes left, and I want to introduce nucleophiles and electrophiles, because that's really the next section that we're going to be doing. And it's very similar to acids and bases, but what I'll do is, instead of introducing the whole topic, I'm just going to give you a little slice right quick.
We gonna get off class 10 minutes early today?
5 minutes. Give me 5 more minutes, and I'll let y'all go and play in the rain or whatever you're gonna do. So I do want to. I just don't want to abandon it, because I rather introduce it and then send videos rather than just sending videos right away. Even though I'm gonna send them after class anyway. But the concept of nucleophiles and electrophiles is very closely related to acids and bases. All right, so a nucleophile, another way to term that is what we call a Lewis base. I think I already introduced that term to you, or an electron donor. And an electrophile is what we call a Lewis acid, or an electron acceptor. All right, so those two things are it's really important to kind of grasp the concept of nucleophiles and electrophiles, because really everything from this point forward, all the reactions we learn and all that, is going to be based on these principles that we learn about nucleophiles and electrophiles. So let me just give you a generic overview real quick, and then I'm gonna stop. Give me about 2 more minutes. So another concept to understand when we talk about nucleophiles and electrophiles is the concept of source to sink.
Dr. Russell, can you go back up a little bit, please, for a second?
Is that good?
Yes. Okay, thank you.
All right, you're welcome. So another concept again is source to sink. Now I want you to think about this in terms of, right, what a sink is. A sink is something that's kind of emptied out, right? And the source we're gonna say is like a stack of dishes, right? So you always want.
Help Desk. This is Ty. How can I help you?
I already was on the phone with you. It's great.
All right. So the stack of dishes here can fit into the sink because the sink is empty, right? The same idea applies to nucleophiles and electrophiles. What an electrophile is, if it's an electron acceptor, right? What it is also electron deficient. So electrophiles, electro meaning electrons, philes from the Greek word philos for love. So this is a lover of electrons, right? So electrophiles they want electrons. They are what we call electron poor. They're electron poor or electron deficient. And then nucleophiles are again nucleo meaning nucleus or nuclei, and then philes meaning from the Greek word for love, or one of the Greek words for love, philos. So this is a lover of nuclei. And so if the electrophiles love electrons, nucleophiles love nuclei, because the nucleus of an atom is protons and neutrons. So it loves positive charges or partial positive charges. So it loves nuclei, right? So nucleophiles, instead of being electron poor, we say they are electron rich. So rich, electron poor. Nucleophiles are sources. Electrophiles are sinks. So the nucleophiles bring dishes, the electrophiles take dishes, right? If you think about the source and sink concept. So if I were to attach an illustration over here, I would say this is my nucleophile, and you abbreviate it NU with 2 with a pair of electrons over the U, and then this is my electrophile. I just call it, I just illustrate it by writing E+. All right, I'm gonna stop right there. Does anybody have any questions about anything? Stop the recording too.